servos, I need to have full control of them. Is what makes it-
All right, talk me through this here. What are we gonna do? So what do you think? What are we gonna do here? Differentiate. Okay, for sure we're gonna differentiate. Before we even do that, maybe there's one thing, and it's just so obvious, I can see why people wouldn't even. Say it again? Domain, good. What's the domain? Good, good. So we know the domain here is all reals. Good. So now we'll differentiate. Okay, to differentiate, talk to me about that. What are our options? What do you choose to do? Say it again. Product rule. Good. Yep. 'Cause it's product. Okay. That works. Can we make things a little easier?
Distribute x.
Yeah, why not? Right? Because this is an easy one. If I distribute the x cubed, I'm just going to get, it's really simple to do because this factor is not taken to a power. I don't have to expand anything. It would be harder if this were like x times the quantity x minus 3 cubed. Then I'd say product would probably be a great idea, right? Because then to distribute, we'd have to, we can't just distribute over, let me write that out. I want to make sure everybody understands this. If we had something like this, if we had f of x equals x times the quantity x minus 3 cubed, everybody gets I can't distribute there, right? Because this is being taken to a power. Somebody defend that real quick. I know you know probably that you can't do that, but why? How would you explain that to somebody who's not in calculus? Why you can't do that? Why this is not equal to x squared minus 3x cubed? Okay, good, because the x minus 3 has to be multiplied by itself first, doesn't it? Really, this is just an order of operations thing, isn't it? Right? If we look at order of operations, we're just simplifying, right? By trying to expand this out. And we have to follow that order. We have to, right? So we'd have to do, first of all, we'd have to take care of that exponent before I multiply it. So I would have to expand this out first and then multiply through. That might be fine to do. I mean, it's not hard because we know x minus 3 cubed. Do you remember what the pattern is for that? I don't want to get off too far on this tangent, but it's all, we're just talking math. This is all good stuff. What's the pattern for a minus b cubed? You remember? Get you started. A cubed. Remember this like a Pascal's triangle thing? 8 minus 3 a squared b. Remember this plus 3a b cubed, or sorry, squared, minus b cubed. So you could, if you remember that pattern, you could pretty easily just expand this and distribute the x. But that's harder. My whole point of this is that's harder. This is easier to do, right? Because in this case, the x is being cubed. That's monomial. No big deal. X minus 3 is to the first power, so I can easily just distribute here. You guys get the difference there? Boy, this is definitely, in my mind, this is one where you would for sure want to just rewrite f of x as x to the 4th minus 3x cubed, and that becomes a really simple derivative, right? So Evan, what's the derivative? If I just differentiate term by term.
4x cubed minus 9x squared.
Good. Okay. And we can factor that. What do we get if we, we can refactor that really quickly then. So in factored form, what do we get?
X squared
Times
b with 4x.
good 4x minus 9. So we wrote it there in factored form, okay? We're going to go ahead and, we're asked to find inflection points here, right? So we have to take a second derivative. Now, what if, this is a big what if here, what if we hadn't been asked to find inflection points? So let's just assume, oh, that didn't work very well at all, did it? Come. green. Oh, well, I don't know. Never mind. It's trying to be tricky. So what if I was just trying to block that out? So what if, I know what I can do. This will be easier. It can be tricky. There we go. So what if I did that? Find all relative extrema. Would you take, Nick, what do you think? Would you take a second derivative there? If you were only looking for relative extrema?
No.
Okay, what would be the advantages? I can see why you say no, because why do the extra work when you could find relative extrema by doing first derivative test, right? Okay, but think about this. How easy is it to take a second derivative here?
Really easy.
Really easy. If I use that form right there where it's a polynomial, it's really easy. And which is easier to use, the first derivative test or the second derivative test? Second derivative test, right? See what I'm saying? You want to work as far down as you can. So here's kind of a general rule. If it's convenient to take a second derivative, always do it. If it's hard to do and you're not specifically looking for inflection points, then don't, right? If this were something like a radical, or if this were a quotient or something difficult to work with, right, or a bad trig function, then you wouldn't do it. But in this case, even if we weren't looking for inflection points, I would say in this case you do take the second derivative because it's so easy to do, okay? So we take the second derivative, what do we get? What are we going to get for that? Minus 18x. Now notice that, of course, and I mean I'm stating the obvious here, but we want to differentiate the polynomial form of the first derivative before we factored it. Why do you suppose we factored the first derivative? So we can find the zeros easily. Right, that's the only reason, right? And so if we factor this one, what do we get? I can take out, in fact, I can take out 6x, good. Leaving me with what?
2x makes 3.
Okay, right, makes sense? Okay, so now we've got all our derivatives. Let's find our critical numbers. So the first derivative equals 0 at what?
0 and -4.
Okay, and the second derivative equals 0 at
0 and 3x.
Okay, good. All right. And these are polynomials, so everybody agrees there's no place undefined. Everything's right. No undefined derivatives. So now we can make our table. All right, so for our table, we got the x row, and go all the way down to f double prime. Our domain, remember, it's all reals. And let's put in our critical numbers. So we get 0 and 9/4. Let's see, that's bigger than 3/2, isn't it? So 9/4 is out here. And then we got 3/2 in here someplace. Okay, so 0 and 9/4 are zeros of the first derivative, right? And 0 and 3/2 are zeros of the second derivative. Okay. Where do we want to work in our table here? Yeah, as far down as we can. Okay, so what are going to be our test points then? Okay, what points are we going to check values of the second derivative at? So 9/4 for sure. Right? 9/4 is our calculus way of killing two birds with one stone. We get to evaluate a test point for the concavity to the right of this critical number while determining what's going on at this first derivative critical number, right? We get two things at once. So what is, if we look at our second derivative in factored form, let's look in factored form, what's the sign of the second derivative at 9/4? We're going to get positive times positive, right? Okay, so this guy's positive. So what's going on there?
Minimum.
It's a minimum. I've got a 0 first derivative. So we know it's a horizontal tangent line, and it's positive, so it's a happy function. So it's a minimum. Okay? Where else? Another test point.
2.
Say it again.
1.
1 would be good. Yeah, we got to pick a value between 0 and 3/2, don't we? So let's just pick 1. What's going to be the sign of the second derivative at 1? We're going to get positive times negative. So that's negative. Okay, so what's that make this then? This guy right here. Ah, inflection point. How come?
It goes from positive to negative.
Okay, good. Point of transition of the second derivative. Negative concavity to positive concavity, right? So this is inflection point. Okay, another test point.
-1.
-1. Okay, and at -1, what's our sign of the second derivative going to be? Negative times negative is positive, so then what's that? Inflection point, yeah. Okay, and let's just take a look at the graph of this thing and make sure that it all makes sense. We could throw in a couple, if we want to throw in some points too, you know, some ordered pairs, I guess we could do that. So how about, what do we get at 0? What are the coordinates at 0?
0.
0, 0. So there's a point. 3/2, is that easy to do? Well, not super easy. Well, we won't worry about the other ones. We got 1, that's good enough. Okay. Okay, so there's a summary in our table. Now let's look at the graph and see what this thing looks like. So it's x cubed times x minus 3. Okay. So there it is. Let's see if that makes... There we go. I got to zoom in or zoom out a little bit, huh? I'm going to go ahead and just change, let's compress this thing vertically a little bit. Stretch it out horizontally. See what I did? I just tweaked it a little bit so we could see the behavior a little better. Okay, so let's take a picture of that guy and let's compare him, see if that makes sense. Okay, does that make sense? Inflection point at 0, 0, there it is, right? And we had positive concavity to the left of that. Well, that makes sense, right? Bowl-shaped up. We've got negative concavity going towards another inflection point at 3/2. So right there is another inflection point, right? We're going concave down to concave up. And then we had our minimum out here at 9/4, so 2 1/4 is about right there, isn't it? Fits, doesn't it? And then after that, well, and then it's bowl shaped up everywhere here, right? Okay, good.
Well,
Question?
in between 0 and 3/2, isn't it technically bowl down?
Say it again.
It's bowl down from negative, from
From
0 to
0 to
3/2.
3/2, yeah, it is, from there to there. So if we look at the places where the concavity is shifting, let's just kind of break this thing up into transitions of concavity. Right, so over here we're positive, in here we're negative, over here we're positive, right? So that matches the behavior, right? Okay, questions on that? Yes?
Is it, will it remain the same concavity all the way to infinity?
Yeah, it will, yeah, it never changes. And how come?
There's no other inflection.
There's no other critical number for the second derivative, so it can't change any place. Okay, yes?
Is the critical number from the second derivative always like the square root of the first derivative?
Is it always a what?
Like 3/2 is the square root of the square root.
Oh,
Is it always
no,
like that?
no, just an accident for this one, yeah. Okay, let's look at another real simple function, but I picked this one for a reason. I wanna illustrate something here. Okay, it's very simple, right? We all know what that looks like, right? That's gonna look like kind of a squared off parabola. So we already know what it's gonna look like, but let's do the calculus here. What's the domain? Yeah, all reals, okay. So derivatives. What's f prime? F double prime? Say it again? Okay, so if we make our table on this one, the critical numbers are all at 0, aren't they? Right? First derivative and second derivative both equal 0 at 0. Okay? So how do we interpret this? Okay, so there's our critical number, and we get zeros for both derivatives, and for y also, for f. Okay, so we know the points at 0, 0. So what do we need to do to determine what's going on here? So you can think about this what does this tell us? If the first derivative is 0 and the second derivative is 0, the second derivative test has failed there, hasn't it? Right? Second derivative test tells us that we'll just pick the sign of the second derivative, and that tells us what's going on at the first derivative. Okay? But we got a 0. 0 doesn't have a sign, and so it failed. And so we have to go back and look at test points in this case on either side. All right? So what would be convenient test points?
-1 and 1.
-1 and 1, sure, why not? -1 and +1, okay? So let's do some stuff here then. What's gonna be, let's fill out let's use these test points for both functions and see what we get. So in the first derivative at -1, that's an odd function. What's the sign of the first derivative there? Okay, it's negative, and then up here it's positive. Okay, so this clears it up. What's going on there? Well, this is the first derivative, though. So it's a what? It's a minimum, isn't it? We're going from negative to positive, okay? Let's look at what happens in the second derivative with those. If we bring down these test points and look at the sign of the second derivative, it's an even function, so I'm just getting positive for both, right? Okay, either one of those rows tells us exactly what's going on. Okay. Is this an inflection point?
No.
It's not an inflection point. Okay. So what is, explain this one to me. How is it that you can have a concavity that for all values less than 0, the concavity is positive, and for all values greater than 0, the concavity is positive, but the concavity equals 0 at x equals 0? Just ponder that for a second. Does that seem weird to you? Does that seem strange?
Is it because it's the slope is 0, so there is no concavity at that point?
No, because we've seen examples where the slope can be 0 and there is concavity, right? Like the last example we looked at. We'll just look at the table for the last example.
No, it's because I was saying because the slope of the second derivative is 0.
Right. Right. The second derivative is 0. So here's an example where the first derivative is 0, the second derivative is not. But yeah, but that's what I'm saying. Does that make sense? What does it mean? What does concavity mean? I mean, concavity, can you have a concavity at a point? You really can't, can you? Because the concavity, just by the nature of what it is, it depends on the relationship between a point and its neighbors to the left and the right, doesn't it? Right? So doesn't that really not make sense even to put a 0 concavity there? I mean, mathematically, that's the way the derivatives work out. But if we look at a picture of this thing, let's just pull up Desmos for a second and look at a picture of what this function looks like. So there it is. That's our function, right? What's it doing? Let me just, oops, undo all my tweaking. All right, so there it is. I can even zoom in a little bit. That's our function. It's like a squared off parabola. You can see that the tangent line pretty clearly is flat at 0, 0, right? But the concavity, if I zoom in and zoom in and zoom in, look what happens. I mean, it's going to look kind of squared off, but there's only one place there where it has a horizontal tangent line. That concavity really is positive at 0, isn't it? Right? It has to be. It has to be. And it has to be because think about its neighbors. As x, if we think of x as being a vanishingly small positive number, the y value is still positive, isn't it? Right? Because f of x equals x to the 4th. It doesn't matter how small a number I take to the 4th power. I'm getting back a number, right? Not 0. Everybody agree? Same thing if I take a vanishingly small negative number. So no matter how small the step the ant takes to the left or the right, he's always going to be higher than he was at 0, 0, right? So that really doesn't make any sense mathematically. I mean, and this is, I like bringing this stuff up because it helps you maybe see that math is not, there aren't necessarily right and wrong answers in math like there used to be, right? There used to be, in Algebra 1, there was a right answer for every problem you did. But what about this one? We could have a debate about this with other mathematicians, and there would be people that would say, well, the calculus tells you that it's 0, and so it's, it really is a 0 value for the second derivative there. So it's, it doesn't have a concavity. I would argue the opposite. I would say if you have a concavity of 0 surrounded by positive concavities, that those essentially cancel out that 0 and make it positive. The nature of the derivative there is that the nature of the function is that it has a positive concavity everywhere, right? You see what I'm saying? I mean, it's a discussion. It's not something that I think you could say is definitely this way or that way. That way just really makes more sense to me. And I think probably most people would agree with that. Okay, so, but we didn't really need that row because up here, the first derivative test resolved the problem, right? It was definitely going from negative first derivative to positive first derivative, and so we know what that means. The first derivative test tells us we've got a horizontal tangent, and we're doing that, right? Okay, what about this function? Let's take x to the fifth. Very similar. But tell me how you're going to interpret this one. So, what's the first derivative? Second derivative? Same issue, right? I get zeros for both derivatives at x equals 0. So our table's going to look almost identical. Same test points, right? So this time, for the first derivative, what's the sign on either side? SIG. Positive, positive, right? So this fails the first derivative test, doesn't it? Right? It's definitely not a maximum or a minimum. What do you think it's going to be? An inflection point. And we can see that from this other, from row 4, can't we? Right, from the F double prime row. We're going to get a negative second derivative there and a positive there. So this is unquestionably an inflection point. Yes?
If we differentiate it further, would that help that?
Not really, because what does it mean? It kind of starts to lose, it kind of starts to get so dissociated from the real graph that it's really hard to make a connection. See, we know what, I mean, we can make a mental connection. We know first derivative definitely corresponds to slope, the tangent line. That's something we can conceptualize easily, right? Second derivative corresponds to concavity. What's the third derivative? The rate of change of concavity. That's pretty hard to see what the rate of change of concavity is going to look like, right? That's one that we don't really, it's not useful to us, okay? And then we know what this would look like, right? If I were to graph this, then it has to be, it's just going to be something like, it's going to be a squared off cubic function. It's going to look kind of more like that.
What was the fifth derivative? Or like the fourth derivative?
So the fourth derivative is going to be the rate of change of the rate of change of the concavity, which once again, it's just so arcane and bizarre that we don't really make a connection to that. It's not really useful to us in terms of what the shape of a graph would look like.
Has anyone ever studied this?
Oh, yeah, I mean, you can, but it's just not, you know, I mean, it's just really not useful probably to spend a lot of brain cells trying to make that connection when it's just not very useful as a tool for us. Okay? Okay, last one I want to do, this one. Okay, I picked this one for a reason. This is, textbooks never do this problem, and there's something really significant that comes out of this, because there's, if you look at all the problems in our book or all the problems in the online one, they never really address what happens with a function like this. So what, you tell me, what do you think's going on here? What's the domain of this thing? All reals, yeah. Right, we got an odd root, so there's no restriction to what values we can put in an odd root. What's the first derivative?
5/3 x to the 2/3.
Okay, and what are the critical numbers of the first derivative then? 0, right? Only one critical number. At 0, it equals 0, right? Okay, so okay, let's look at the second derivative.
And divided by 9 times 3 of x.
Times x to the
Negative 1/3.
negative 1/3. So we could write that as 10 over 9 x to the 1/3. Okay, so what's going on there?
X can't equal 0.
Okay, so we have a critical number there where the second derivative is undefined at x equals 0, right? So it's a different kind of critical number. Let's make a table out of this one. So 0, our function is 0 at 0, right? And then we get a first derivative critical number and a second derivative is undefined. All right, so then the second derivative test fails here, right? We don't get, we don't get a sign for the second derivative, so we need test points. What we would probably use.
-1 and 1.
Okay, let's just check. Let's check. We're going to work in the fourth row, aren't we? Right? In the F double prime row. So what do we get at -1? Positive or negative? Second derivative. Negative. Okay. At +1. Positive. So what is this? So it is an inflection point, right? And the point I want to make with this is that you can get, you don't see this very much at all, but you can actually get, because usually what's going to happen is if the second derivative is undefined at a certain point, well, the first derivative and maybe even the function have already been undefined there, right? And so it's usually not as useful. Like if the function's undefined there, it's going to be a vertical asymptote, and so it's not even a critical number, right? But here's an interesting function because this is one where the function and the first derivative are both defined at 0, but the second derivative is not. And the point I want to make here is that this can be, you can get critical numbers that end up, that end up not being false positives, that, that really work. You can get critical numbers of the second derivative where the second derivative is undefined. Right? So this is definitely an inflection point. Let's look at a graph of this thing. Okay, so what was it, 5/3? So there it is, right? That's an inflection point, isn't it? Everybody see it definitely goes from concave down to concave up. Are there any, do you notice any, and I'm asking you, I mean, I don't really know that there's an answer to this. What's your impression of the shape of this thing? If I zoom in, do you see any differences between an undefined inflection point and a 0, an undefined critical number that proves to be an inflection point versus a 0 critical number that proves to be an inflection point?
Will you put x to the 5th up there?
Say it again.
Will you put x to the 5th up there?
Sure. Oh, yeah. Compare it. Yeah. That's a good idea. And I'll put x cubed up here, too. Yeah, it does, doesn't it? It almost seems like it's a little bit of a sharper, which makes sense, doesn't it? It's like it's a more abrupt change in the concavity. Now, that's my impression too, is that you get that look to it. It's like it goes from being pretty strongly concave down to being pretty strongly concave up, just instantly, right?
Are they all cross?
They all equal 1 at 1.
What's the question, Nick?
Cross the same spot.
Well, yeah, just because they're all monomials, right? So they all have zeros at 0. But that's, I mean, what, I don't know that there's, maybe that's just our minds playing tricks on us, but that does seem to be the impression to me too,
I
right?
meant like F1, but I understand why.
Oh, yeah.
They have one,
Yeah, okay. Okay, what if we put up x to the 2/3? Okay, look at x to the 2/3. Okay, that's a weird one, right? How much time we got?
2 minutes.
Oh, man. Dagnabbit. Okay, that's another fun one to look at, x to the 2/3. Just by looking at the graph, What's going on at 0, 0 for the orange function?
Sharp corner.
Okay, it's a sharp corner, right? It definitely is a valley, though, isn't it? Right? It's definitely a relative minimum. It's going to be an undefined first derivative, and therefore also it has to be an undefined second derivative. But it is
Concave down.
it's concave down the whole time, isn't it? Right? Does that make sense? So it's definitely not an inflection point. Here's a challenge for you. Can you come up
would that
with...
one not have any inflection points or relative extrema?
Say it again.
Would it not have any inflection points or relative extrema?
The orange one?
Yeah, the orange one.
Relative extreme at 0, 0. Yeah. Okay, here's a challenge I'll give you right now for break. Can you come up with a function that has a point that is simultaneously an inflection point and an extremum? Ooh, never asked anybody to do that before. Can you come up with a function? Well, that's my challenge to you. Can you come up with one that does that?
Does it have to be, can it be relative extreme?
Well, that's what I mean. It has to be a relative extremum and an inflection point at the same time.
Could you say it's also an endpoint?
No, not an endpoint. Can't be an endpoint. It has to be in the middle of the